Today we're going to take a look at how to manipulate terms with logarithmic values in it. And everything's going to be based on these three properties. So you see right in front of you that if I have a product of two terms, then that can be split apart into the sum of its factors with the same base. If I have a division of two terms, that can be equivalent to the difference of the numerator minus the denominator, once again having the log of the same base. Last but not least, if I have the log of some quantity to a power, that's equivalent to taking that power, bringing it out in front of the log, and multiplying it by the log with that same base of that term. So what we're going to do is we're going to go through and manipulate a whole bunch of terms today. So in these cases we're going to have a string of terms, and we're asked to express that string in terms of a single logarithm. So we see here that we have log base 3 of 5 plus the log base 3 of 4. Key thing is that I have the same base. These are added, so I can combine that to a product of the two. So this is the same as the log base 3 of 5 times 4, or the log base 3 of 20. Now you'll notice here, in this case, 1/2 is multiplied by the natural log of 25. However, that 1/2 is not multiplied by the natural log of 2. So what I'm going to do is use that third property, except go backwards on it. I'm going to take that multiplication and bring it up to a power. So this is the natural log of 25 to the 1/2 power minus the natural log of 2. Now, the 1/2 power is the same as the square root, so this is the natural log of the square root of 25 minus the natural log of 2. Natural log of 25 is 5, or square root of 25, sorry, is 5. And I'm going to subtract from that the natural log of 2. Since I have a subtraction, that can go to a division. So that's the natural log of 5 over 2. Very similar. In this case, I have an addition followed by a subtraction, and then there's a multiplication within that. So what I'm going to do is I'm going to take this multiplication, bring that into a power, and then deal with this sum first. So this is the log base b of m times n minus the log base b of p to the cubed, or raised to a third. Since this is a subtraction, that goes into a division, so I have the log base b of m n over p cubed. You'll notice in this term, I've got a set of parentheses, so I'm going to do that first. I can bring this 2 up into a power, so I have 5 log base 2 of ab minus the log base 2 of c squared. Now I'll take this 5, bring it up into a power. I have the log base 2, sorry, forgot to write that, of ab, quantity to the 5th, minus the log base 2 of c squared. Subtraction goes to division, so this is log base 2, and I'm going to just bring this power of 5 into both of these terms. Remember, power of power, we multiply the powers, so that's a to the 5th, b to the 5th over c squared. Now in this case we have a single logarithm, but we're going to expand this into a set of sum and differences. So we're going to go just the opposite way, and we're going to express any powered term as factors or multiplications. So in this case I have that division, which I can split into a subtraction. So this is the log base b of the quantity of 2x plus 1 all to the third power minus the log base b of the quantity of 3x minus 5 to the fourth power. Each of these powers can be brought to the front by that third rule, leaving us with 3 log base b of the quantity of 2x plus 1 minus 4 log base b of the quantity of 3x minus 5. In this problem we have a division to start with, and then there's a square root here. We've used the square root before in terms of powers, so let's rewrite this. We have the log base b of the quantity of x minus 1. Square root is a half power, minus, because I have the division, log base b of x cubed. And we remember in these cases, powers go to the front, so I have a half times the log base b of the quantity x minus 1 minus 3 times log base b of x. So there's a different spin on the expansion now. We have the logarithm of a single term, the log base b of 30, but we're given some indicated values for what log base b of certain numbers are. And they want us to find a numerical value for the log base b of 30 and then the log base b of the cube root of 2. We know 30 is simply the log of 5 times 6, which goes to log base b of 5 plus the log base b of 6. Unfortunately, there's no 6 here, but I have a 2 and a 3. So this is the log base b of 5 plus the log base b of 2 times 3. And I'll split this multiplication into the sum of two separate logarithms. So this is the log base b of 5 plus log base b of 2 plus the log base 3 log base b of 3. Each of these has a numerical equivalent. That's 1.61 plus 0.69 plus 1.1, which gives us a total of 3.4. Moving over to this problem, I can rewrite this in terms of an exponent. So this is the log base b of 2 to the 1/3 power. 1/3 can move out in front, so this is 1/3 times the log base b of 2, and I have a known value for the log base b of 2. So this is 1/3 multiplied by 0.69. That's going to equal, what, 0.23? Now we're going to be asked to solve some logarithmic terms. In a simple case, if I know the log base 3 of some value is equal to the log base 3 of 7, well then, like we did in our exponential problems, if we have the same base, in this case if we have the same log base, 3 in both cases, then the two quantities have to be equal. So I can basically eliminate the logarithm terms and just say x is equal to 7. Now in this case I can't do that quite yet because I don't have the log base 5 of one quantity equaling the log base 5 of another. I have to make sure I have the log base 5 of one term on the other side and the log base 5 of another term on the other side. Then I can eliminate the logarithm terms. In order to do that, I'm going to take this 2 and move it up to the power. So I have the log base 5 of x squared minus x minus 2 is equaling the log base 5 of x minus 2 quantity squared. Now I have the log base 5 of one term equaling another, so I can eliminate the logarithm terms, have x squared minus x minus 2 equal to my FOILed out version of this, which is x squared minus 4x plus 4. The x squareds will go. I get 3x over here. I get 6 over there. So x is equal to 2 in this case. So in our last problem, we notice we have an isolated logarithm term on the right side, but several logarithm terms on the left. We're going to need to combine all these in order to say the log base b of one term is equal to the log base b of another. In each of these cases, I'm going to need to bring the multiple up to the power. So this will go to the log base b of 4 to the 3 halves minus log base b of 8 to the 2 thirds plus the log base b of 2 squared. 2 squared is going to be the easiest to handle. The rest we're going to have to use our knowledge of rational exponents. So this is the log base b of the square root of 4, square root of 4 cubed minus the log base b of the cube root of 8 squared plus the log base b of 4. And that's all going to equal the log base b of x. Square root of 4 is 2, cubed is 8, so this is the log base b of 8, minus cube root of 8 is 2 squared is 4, log base b of 4, plus the log base b of 4 is equal to the log base b of x. Log base b of 4s are eliminated because I have a positive and a negative. This leaves me with log base b of 8 equals the log base b of x, so therefore 8 must equal x. That's all we've got. Fill out the lesson summary, do the MyMathLab problems, and we'll see you tomorrow.